Out in a quiet corner of the cosmos, a seemingly ordinary galaxy hides a black hole 17 billion times the mass of the Sun, shaping an entire group of galaxies in near total silence. Tonight's journey slowly drifts from the outskirts of that group down to the very edge of the description-forbidden core where light itself struggles to escape. If this kind of calm, science-filled voyage helps you relax and fall asleep, please gently tap like subscribe and turn on the bell so more tranquil nights among the galaxies can follow. In a quiet patch of the constellation, Eridanus NGC 1600 glows as a smooth pale ellipse against the dark. At first glance it looks like an ordinary massive elliptical galaxy. Its calm appearance hides a black hole with a mass of about 17 billion suns, a mass that stretches current ideas about where such giants belong. By the end of the journey, the layered structure of this system will be familiar. It will show how such an extreme object can live inside such a seemingly modest, quiet group. This contrast between appearance and hidden heart forms the thread that guides the whole story. It becomes a gentle map of how such giants can grow in unexpected places. Far away from the bright centre, the surrounding galaxy group stretches out in long, faint arcs of light and small, hazy smudges. A handful of companion galaxies drift in the shared gravitational well, their paths slow and wide over billions of years. The scene resembles a quiet countryside of galaxies rather than a crowded metropolis, with generous dark spaces between each island of stars. This sparse setting matters because most known ultramassive black holes sit in the brightest galaxies of rich clusters, not in environments as calm as this. Against that low-density background, NGC 1600 rests near the middle of the group, shining more strongly than its neighbours but still appearing restrained. Through large telescopes it shows the soft, featureless glow typical of an old elliptical. There are no spiral arms, no sharp dust lanes, and no brilliant blue knots of current starbirth. Its overall colour leans toward gentle reddish tones. This is the signature of an ancient population of stars that long ago used up most of the cold gas available for new generations. The galaxy looks settled and unhurried, as though most of its dramatic reshaping events lie deep in the past. That settled look carries weight because it hints at long periods of quiet after earlier phases of vigorous merging and feeding. Light from NGC 1600 travels roughly 200 million years before reaching present-day instruments. Every observation captures a scene rooted firmly in distant cosmic history. Whatever collisions, inflows and outbursts built this system have already played out. They leave behind only their imprints in the arrangement of stars' gas and dark matter. This distance in time offers a gentle sense of safety. The galaxy becomes a record to be read, not an active threat to be feared. The more carefully astronomers measure that light, the more clearly a sequence of layers emerges. Each region carries its own clues about how the system grew. On the wider scales, the entire group sits inside the dark matter halo. This region extends far beyond the visible edges of every galaxy in the group. Its mass outweighs the stars by a wide margin, yet it leaves no direct glow. This halo is a vast invisible cocoon, whose gravity gathers galaxies and hot gas into one bound structure. The halo itself cannot be seen directly. Its presence is traced through the motions of the galaxies and the glow of X-ray emitting gas that fills the spaces between them. This deep gravitational well sets the overall rhythm guiding the slow fall of matter toward the centre over many billions of years. Within this halo, the outer parts of NGC 1600 blend gradually into the group environment. They form a broad stellar envelope that fades gently into the dark. Stars in these outskirts move in long, slow orbits. Their paths trace the combined pull of the galaxy and the surrounding halo rather than responding to local details. Their distribution hints at past mergers where smaller galaxies were stretched, stirred, and gradually absorbed, leaving behind faint wings and fans of light. Even when these structures are barely visible, they still whisper that the system was once more active than its present calm suggests. Each absorbed companion would have contributed not only stars but also gas. In many cases, it would also bring in its own central black hole to the growing main galaxy. Over time, this steady gathering builds the visible body of NGC 1600. It also builds the conditions needed for an exceptionally massive black hole to develop at its core. The gentle light now seen in the outskirts is therefore more than decoration. It is the outermost page of a long-layered record written in starlight. From this wide, peaceful view, the narrative begins to turn inward. It moves toward regions where the light brightens and the pull of gravity grows stronger. Ahead lie the luminous envelope, the inner bulge, the shallow central core, and far inside the unseen domain of the black hole itself. The promise of the journey is simple and unhurried. By moving steadily through these layers, the connection between the quiet group, the massive galaxy, and the extraordinary object at its heart becomes clear. That understanding arrives without strain as the story lingers at each layer and lets the details settle. The galaxy group around NGC 1600 feels spacious rather than crowded, a loose association of members spread across a wide dark background. This gentle setting matters because it contrasts with the busy turbulent clusters where such extreme black holes are usually found. The difference in environment becomes a quiet clue that there may be more than one path to building an ultramassive heart. On the sky, the group appears as a scattering of faint smudges surrounding the main elliptical, with large stretches of darkness in between. Each of those companions holds its own stars and history, yet their number is modest compared with the throngs in rich clusters. The scene resembles a small town of galaxies rather than a glowing city of hundreds. That shift in crowding hints that the growth of the central galaxy and its black hole follows a different rhythm. Systems born in denser regions grow under other rules. The galaxies in this group move in long, slow orbits set by the shared dark matter halo. Over billions of years, these paths carry them past one another in repeated gentle encounters. Some pass close enough to feel strong tides gradually losing stars and gas to the main elliptical. Others remain on wider tracks only lightly disturbed. This pattern of occasional mergers and long stretches of calm growth helps explain why the group looks sparse today. Many of the smaller systems that once filled this volume may already have been stripped apart and folded into the envelope of NGC 1600. That history matters because every galaxy that falls inward brings new material and sometimes its own central black hole. In rich clusters, such processes happen amid continuous harassment and rapid encounters. In a group like this, events are rarer, but can be more efficient with fewer outside disturbances to pull material away. The group acts as a quiet funnel guiding a select set of galaxies toward the center. This flow allows the main elliptical to gather mass early and hold it. This slower, cleaner growth channel may be one reason a black hole so large can form without the noise of a giant cluster. Surrounding the galaxies, thin gas stretches through the group, aligned with the deeper dark matter structure. At the temperatures traced in X-rays, this gas glows faintly and fills the gaps where no stars shine. It settles into the shared potential well thicker near the center and more diffuse farther out. Even when invisible to the eye, it plays an important role. It can cool over time, drip inward, and briefly feed new activity in the inner galaxy. It can also remain hot, held aloft by energy released as material falls into the central region. Either way, the group-scale gas connects the outer dark halo to the inner galaxy, forming another layer in the nested structure. The shape of the group reveals that its dark matter halo is quite concentrated. More of the mass gathers toward the center than in many equally massive systems. This concentration deepens the gravity felt by the galaxies and the gas. It helps keep them bound and makes it easier for material to drift inward over long spans of time. In a gentle way, the entire group seems to lean toward its center. That overall tilt supports the idea that mass inflow has favored the central galaxy, allowing it to grow disproportionately compared with its neighbors. Over time, this imbalance would leave one dominant elliptical surrounded by smaller satellites, which is precisely what current observations show. The brightness ranking of the group underlines this point. NGC 1600 outshines the second brightest member by a generous margin. Astronomers sometimes describe such systems as fossil groups, where most of the original bright galaxies have merged into a single central body. In that picture, the group once resembled a more even collection of peers, but slow mergers gradually erased this balance. What remains is one large old galaxy that carries the memory of many smaller ones in its stars and in the black hole at its center. Within this setting, the absence of strong present-day activity becomes another quiet clue. There are no powerful radio jets stretching across the group, no glaring quasar beacon at the heart. Instead, the system invites patient reading. Each galaxy's position, brightness, and motion offers hints about how and when earlier mergers occurred. Taken together, these signs suggest a past that was busier than the present scene implies. In that sense, the sparse group environment does not weaken the case for an ultramassive black hole at the center. It strengthens the case because the system has had long, uninterrupted periods for the central galaxy to claim new material. From this broad view of the group, the narrative turns inward toward the faint outer halo and envelope of NGC 1600. In those regions, the traces of earlier mergers begin to appear more clearly in the light. The light in the outer halo of NGC 1600 lies close to the edge of visibility, a soft mist wrapped around the brighter core. In that faint glow, the story of the galaxy's growth becomes more detailed. The outer stars move in long orbits that feel not only the pull of the central galaxy, but also the weight of the entire group. Their paths help draw the outline of the dark matter halo that holds everything together. Even though each individual star is far too faint to pick out at this distance, their combined light forms a smooth extended envelope that stretches farther than the eye first expects. This outer envelope matters because it stores the memory of past mergers. When smaller galaxies fall in, their stars rarely come to rest in the very center right away. Many are left drifting in the outskirts, slowly mixing into the halo. The faint glow therefore carries the signatures of many former companions now dissolved beyond recognition. Over time their shapes blur, but their contribution to the halo remains. The more massive the envelope, the more mergers and accretion events must have taken place. Around this soft background, a few remaining faint companions still circle NGC 1600. These satellites move in the same shared gravitational well, but have not yet been fully stripped apart. Their shapes may be slightly distorted, stretched a little along their orbits by the tides of the main galaxy. Some follow paths that bring them close in on one side, then send them swinging far out again. Others remain on more circular tracks. Each companion represents a stage in a slow, ongoing process of capture and integration. This mix of dissolved and surviving satellites offers a calm but powerful clue. It suggests that the central galaxy has spent billions of years gently collecting and digesting neighbours. In the early universe, encounters would have been more frequent when galaxies were closer together and gas was more plentiful. In the later universe, as distances grew and gas supplies declined, such events became rarer but still significant when they occur. The outer halo and its companions are therefore not only decorations, They are evidence that the galaxy did not form in isolation, but through repeated steps of gathering and merging. The halo also smooths the transition between the group and the galaxy. At large distances, the brightness drops to levels that match the general background of intragroup light, where stars no longer belong clearly to a single galaxy. Further in the surface, brightness rises gently, and the light feels more centrally anchored. This gradual change shows that there is no sharp boundary. The system is layered rather than divided, with the dark matter halo, the intragroup light, and the galaxy's own envelope blending into one another. This layered view helps explain how the central region could accumulate so much mass. Matter does not need to fall directly onto the black hole to influence its growth. It only needs to reach the inner galaxy, where subsequent processes can move some fraction further inward. The presence of an extended halo also affects the motions of the companion galaxies. Those that orbit within this region feel a strong, steady pull toward the center. Dynamical friction, the slow exchange of energy between a moving galaxy and the sea of surrounding stars, gradually reduces their orbital speed. Over long periods, this process causes their paths to shrink. The satellites spiral inward not dramatically, but with great patience. As they do, they lose stars into the halo, and eventually into the inner body of NGC 1600. This slow inward drift is one of the quiet engines that builds both the galaxy and its core. Modern observations reveal that the halo of NGC 1600 is not sharply cut off. Instead, it tapers over large distances, indicating that the galaxy's influence extends far into the group. This breadth supports the idea that NGC 1600 has long occupied a privileged position near the center of the dark matter halo. It has had the first claim on many of the systems that wandered into the group's grasp. That long-standing central role helps explain why its mass and the mass of its black hole are so large compared with its remaining neighbors. In a sense, the halo is a quiet census of past growth. It records stars that once lived in many different places, now brought together into one shared structure. From the perspective of the present day, the halo appears serene. The violent processes that created it are long over. Tidal forces that once tore galaxies apart are still at work, but in more subtle ways, adjusting orbits and gently shifting stars. For a listener imagining this scene, the outer halo can be pictured as a dim extended cloud of ancient stars barely brighter than the background sky, wrapped around the galaxy like a loose glowing cloak. From this cloak, the path inward continues toward regions where the signs of past collisions become sharper and where delicate shells and streams of light begin to trace more specific episodes in the galaxy's history. The outer regions of NGC 1600 do not shine as a single perfectly smooth haze of light. When images are stretched and deep, exposures are examined carefully. Faint arcs and ripples appear within the halo. They curve gently around the galaxy, sometimes almost concentric, sometimes tilted or incomplete. These delicate forms are stellar shells and streams, long trails of stars left behind when smaller galaxies were pulled apart. They are fragile structures only slightly brighter than the background glow, yet they carry very specific memories of how the galaxy grew. Each shell marks a place where debris slows and piles up along its orbit. Each stream traces the stretched path of stars that once belonged to a separate system. Together they act as fossil scars written into the outer light of NGC 1600. When a satellite galaxy begins to fall toward the main elliptical, its stars do not all respond in the same way. The host galaxy's gravity tugs more strongly on the near side than on the far side. Over many orbits, this difference stretches the smaller galaxy out along its path. Stars that once moved together inside a compact companion become part of a longer, looser structure. Some drift ahead, some lag behind, but all now move mainly in the gravitational field of NGC 1600 itself. If the incoming orbit is almost straight in and out, the stripped stars slow at the farthest points of their motion and spend more time there. Those gentle pauses show up as shells, thin layers where star density is slightly enhanced. If the orbit is more curved or inclined, the debris can form long ribbon-like streams that wrap partway around the galaxy. Each pattern reflects the shape and timing of the original encounter. The presence of these structures shows that the halo of NGC 1600 is still adjusting to past events. It is not a frozen, perfectly mixed cloud. Instead, it is a region where evidence of individual mergers remains visible for a while before gradually fading. Over cosmic time, orbits wrap and overlap, washing out sharp features. Only debris from relatively recent interactions on the scale of a few billion years leaves clear shells and streams. Older scars become part of the general smooth envelope. This means that the structures seen today belong to the later chapters of the galaxy's life, rather than its earliest youth. They indicate that growth continued after the central parts, and the black hole were already massive. In this sense, the outer scars are careful annotations in the margin of a long, already written story. They refine the sequence without changing the overall outcome. The merging events that produced these scars affected more than just stars. As smaller galaxies were stripped, their gas was disturbed, heated, or funneled inward. Some of that gas may have fed the black hole in earlier active phases, while some joined the hot atmosphere of the group. Dark matter from the satellites also settled into the shared halo, thickening the gravitational field that holds everything together. Even though these processes were once energetic, the signs now appear calm and static in the light. For a mental picture, the shells can be imagined as very faint overlapping rings of starlight. They lie at different distances from the center like soft contours cut into the halo. Streams can be pictured as thin drifting bands fading at the ends, where they blend into the general background. Within them, individual stars follow smooth, predictable paths that take many millions of years to complete. Nothing abrupt happens on human timescales. The entire scene unfolds so slowly that from one lifetime to the next it appears completely still. This quiet appearance matters when thinking about NGC 1600 as a whole. It means the galaxy can be described as a settled system, even though it still carries marks of earlier disturbances. Ancient violence has relaxed into steady patterns. The outer halo becomes a gentle record rather than an ongoing storm. For the narrative journey inward, these shells and streams form a natural bridge between the broad, anonymous envelope and the more regular inner light. They show where the influence of particular mergers can still be traced, yet the global shape is already dominated by the main galaxy. Passing through this region, the view gradually shifts from individual scars to overall structure. The brightness increases a little more quickly with each step toward the center. Gradients in light become steeper, and small inward moves produce larger changes in surface brightness. In that zone, orbits begin to feel more sharply the concentrated mass of the inner galaxy, rather than the diffuse pull of the halo alone. This slow steepening prepares the way for what lies ahead. Deeper inside, the shells give way to a smoother luminous envelope and a swollen central body, where the imprint of past mergers is no longer seen as separate arcs, but as a broad carved core. The path now turns toward those brighter, denser layers, where the connection between missing starlight and the reach of the central black hole gradually becomes clearer. Elliptical galaxies share a quiet look that is easy to recognize. They appear as smooth, rounded clouds of starlight with no prominent arms or dust lanes. Their colors tend to be warm and reddish, signaling that most of their stars are old and that fresh star formation has slowed or stopped. In many cases, they live in dense environments such as galaxy clusters, where repeated interactions strip away gas and stir orbits. A typical massive elliptical therefore becomes a kind of cosmic retirement home filled with aging stars that orbit in graceful, largely random paths. This picture of what is normal sets the stage for understanding how NGC 1600 both fits and bends the rules. In a textbook example, the brightness in an elliptical galaxy declines smoothly with distance from the center. The central regions are very bright with light falling off steeply into the outskirts. Such profiles describe how stars are arranged in 3 dimensions and allow simple comparisons between galaxies of very different sizes and luminosities. They also form the basis for relations that link the mass of a galaxy's central black hole to the overall structure of its host. In a typical case, the mass of that black hole scales in a predictable way with the total mass of the stars and with the tightness of the central light. Another familiar trait of many ellipticals is the nature of their internal motions. Instead of neat ordered rotation like that of a spiral disk, their stars move on orbits that are oriented in many directions. Velocity dispersion is the term used to describe how wide the spread of star speeds is along a given line of sight. A large dispersion means the stars are moving quickly in many directions, supported against gravity, more by random motion than by rotation. This property is important because the dispersion measured near the center provides another connection between the galaxy and its black hole. Galaxies with higher central dispersions usually host more massive black holes, and this pattern helps build scaling relations used throughout extragalactic astronomy. The stellar populations in ellipticals also tend to follow broad patterns. Most of their stars formed early in cosmic history during intense bursts of activity. Over time, the supply of cold gas thinned out, and the rate of new star formation declined. The result is a population dominated by older redder stars with only small traces of younger bluer stars in special cases. Gas physics adds another layer to this standard picture. Ellipticals usually contain little cold gas and dust compared with spiral galaxies. Instead, they sit in halos of hot X-ray emitting gas that is held by the combined gravity of the galaxy and its dark matter halo. This hot gas can slowly cool and flow inward, but it can also be kept warm by energy released from the central black hole or from aging stars. The balance between cooling and heating helps decide whether new stars will form or whether the galaxy will remain quiescent. When astronomers speak of scaling relations, they refer to these interconnected patterns. The mass of the black hole, the velocity dispersion, the total stellar mass and the shape of the light profile all tend to follow tight correlations. For a given host galaxy, these relations predict an expected black hole mass and an expected internal structure. The patterns are not perfect, but they are strong enough that outliers stand out clearly. Such outliers are valuable because they reveal where the simple picture is incomplete. NGC 1600 behaves like a fairly normal massive elliptical in many ways. Its overall light profile outside the very central region falls off in a way that matches common models. Its stars are mostly old, its gas content is low, and it inhabits an environment where mergers and interactions have had plenty of time to act. The velocity dispersions measured in its inner body are high as expected for a large pressure-supported system. The galaxy might be filed mentally alongside many other bright ellipticals in groups and clusters. The quiet colour, the smooth appearance and the lack of obvious spiral features all support that impression. This likeness to a standard case is important. It means that any differences found deeper inside cannot be dismissed as quirks of a very strange host. They belong to a galaxy that by outer measures is almost textbook. The story now begins to narrow its focus from this general pattern toward the inner bulge and nucleus of NGC 1600. In that narrower region, the light profile deviates from the common shape. The central brightness levels off into a broad, shallow core instead of climbing to a sharp peak. That change signals that something has removed stars from the center or prevented them from ever settling there. The next step in the journey explores that core in more detail and considers how the missing starlight relates to the strong unseen gravity of the ultramassive black hole at the heart of the galaxy. Closer to the center of NGC 1600, the smooth glow of the galaxy carries more subtle structure than the eye first notices. If the contours of equal brightness are traced carefully, they do not form perfect circles or even perfect stretched ellipses. They look slightly boxy, with gentle flattening along certain directions. This boxy shape is a quiet but important signal. It hints that the inner galaxy has been shaped by major mergers rather than by slow, isolated growth. Systems formed mainly through the steady settling of gas tend to show more disk-like or disky signatures in their contours. In contrast, boxy isophotes arise when large collisions between galaxies have stirred and scrambled stellar orbits in more violent ways. The light becomes a record of that stirring frozen into the overall geometry. Stellar motions in these central regions add another piece to the picture. Spectroscopic measurements reveal that the stars do not whirl around the center in a fast-ordered spin. Instead, their velocities show only modest rotation compared with the strength of their random motions. Many stars move along elongated or tilted paths that do not line up along a single preferred axis. The galaxy is supported more by the spread of velocities in all directions than by coherent rotation. This pattern reinforces the message carried by the boxy shape. Major mergers between galaxies of comparable mass can efficiently mix orbits, converting ordered rotation into a broader dispersion. Over time, the remnants of such collisions settle into systems that rotate slowly and show little sign of disk-like structure. The result is an inner region where stars take many different routes around the center, all held by the same gravitational potential. In NGC 1600, this potential is deep and extended, reflecting both the mass of the stars and the presence of the dark matter halo. At the same time, it is already influenced by the huge mass of the central black hole. Even at distances where the black hole does not yet dominate the total gravity, its presence gently shapes the allowed orbits. Stars that pass too close can be scattered or removed. Others adjust their paths to avoid those dangerous zones. Over long periods, these processes carve out preferred families of orbits and reduce the number of stars following nearly circular tracks. The result is a kinematic field where rotation plays a minor role. Boxy isophotes and slow rotation often go hand in hand with another feature, a central core where the stellar density is lower than expected. In many massive ellipticals, the brightness climbs steeply toward the center if there is no mechanism to remove stars. In galaxies like NGC 1600, the profile flattens instead. The light seems to pause, forming a broad plateau rather than a sharp peak. This is called a depleted core and is thought to form when pairs of supermassive black holes brought together during mergers spiral inward through the sea of stars. As they orbit, they sling nearby stars outward through repeated gravitational encounters. Each ejected star carries away energy and angular momentum from the pair, allowing the two black holes to sink closer together. The overall effect is to excavate a region around the center, lowering the local stellar density. After the black holes eventually merge, the newly formed giant remains, but the missing stars do not return. They stay on wider orbits or escape the central region entirely. The boxy structure and slow rotation of NGC 1600 therefore point strongly toward a past in which multiple large mergers occurred. Each event likely contributed its own central black hole. Over time, these black holes paired up, spiraled together and merged, leaving behind both a depleted core and a more massive single black hole. The present-day shape and kinematics are the relaxed aftermath of those events. They tell a story of repeated inward journeys by satellite galaxies and their central engines. In this way, the inner body of NGC 1600 becomes a kind of echo chamber for past interactions. The geometry of the light and the pattern of velocities together reveal that the galaxy did not grow gently and alone. It grew by absorbing others again and again, and by allowing their central black holes to fall toward the middle. Each merger deepened the potential, well-stirred the stars, and helped clear out the core. Together they built both the broad, shallow central light profile and the ultramassive object now buried inside. Despite this complex history, the present view is quiet. Stars glide along their orbits in a steady, ordered chaos. No obvious shocks or ripples disturb the starlight. The mergers that shaped these motions concluded long ago. What remains is a settled structure that can be read at leisure. For a listener picturing this region, the inner galaxy can be seen as a slightly squared-off glow, not quite round, with stars moving on crisscrossing paths rather than in a neat spin. The impression is of great stability, supported by a deep central gravity well. From these inner motions, the journey now turns outward again, not in distance, but in perspective toward the larger environment of dark matter and hot gas that wraps the galaxy and its group. In that surrounding medium, the long-term effects of the central black hole and its growth become visible on scales far beyond the starlight alone. Around NGC 1600, the deepest layer of the system is not traced by starlight at all. It is traced by gravity and by a very faint, very hot glow. The galaxy and its companions sit inside a dark matter halo, an extended cloud of invisible mass that outweighs all the stars combined. Dark matter halo here simply means a vast unseen structure whose gravity holds the group together. Its presence is known from the way galaxies move, and from the shape of the hot gas that fills the spaces between them. That gas is so thin that no breath could be drawn from it. It is heated to tens of millions of degrees, and therefore shines in X-rays rather than invisible light. X-ray gas is just very hot rarefied material that radiates mainly at high energies. From a distance, this gas fills the group like a soft glowing fog, brightest near the center and fading outward into the dark. The shape of this fog follows the pull of the halo. Where the halo's gravity is stronger, the gas is denser and brighter. Where the halo's pull weakens, the gas thins and merges into the wider cosmic background. Observations show that around NGC 1600 this halo is unusually concentrated. More mass gathers closer to the middle than in many similar systems. That extra central weight deepens the gravitational well, making it easier for galaxies and gas to remain bound. Over billions of years, this deep well also encourages matter to drift inward. The entire group, from its outermost members to its hot gas, leans gently toward the center. The hot gas does not sit in perfect balance. It constantly negotiates between gravity pulling it inward and pressure pushing it outward. Gravity tries to draw it down the slope of the potential well toward denser regions near NGC 1600. Pressure from its own high temperature resists that pull, trying to keep it expanded and smooth. Meanwhile, the gas radiates energy away as X-rays. As it loses energy, it cools very slowly, and cooling gas would in principle begin to sink inward. If this process were left unchecked, dense streams of cooler gas would form and flow toward the central galaxy. They would feed fresh star formation and fuel the black hole. Many systems, however, show less cooling than simple estimates suggest. Something is adding energy back into the gas and slowing its descent. In the NGC 1600 group, the central galaxy and its black hole are the most natural suppliers of that extra heat. Energy released long ago when the black hole was more active could have inflated bubbles, driven weak shocks, and stirred turbulence in the surrounding gas. Even more gentle outflows today, perhaps, in the form of mild jets or winds, can keep the hot atmosphere from collapsing. The balance between cooling and heating becomes a slow, self-regulating cycle. When gas cools too quickly and begins to fall inward, more fuel reaches the central engine. The black hole brightens and pushes energy back into the surroundings. The gas warms, its pressure rises, and the inflow slows. Over long times, this feedback keeps the group halo in a state that is neither fully cooling nor fully static. It hovers in a comfortable, long-lived balance. This feedback matters because it shapes not just the gas, but also the long-term future of the stars. If too much gas cooled and fell inward, NGC 1600 would form new stars and become bluer and more irregular. If too little ever cooled, the black hole would remain permanently starved and small. The present situation suggests that enough gas has arrived over cosmic time to grow the black hole to its current mass. At the same time, enough energy has been returned to the halo to suppress large bursts of star formation in the group today. The result is the quiet reddish system now observed, with hot gas held in place by gravity and mild heating. For a mental image, the dark matter halo and the hot gas can be pictured together as a gentle unseen cushion in which the galaxy floats. The halo itself emits no light, but the gas traces its shape like mist gathered in a valley. NGC 1600 lies near the floor of that valley, where both the concentration of dark matter and the density of hot gas are highest. Companion galaxies glide through this medium, leaving only small disturbances as they pass. Over very long times, friction with the halo and interactions with the gas help draw some of them inward. All these layers work together. The dark halo provides the deep gravitational framework. The hot gas marks that framework and supplies potential fuel. The central galaxy anchored in this structure gathers material and hosts the black hole. The black hole in turn releases energy that influences the gas, and thus the future supply of fuel. In NGC 1600, this quiet cycle has had a long time to operate. It has helped build a black hole that is enormous compared with those in many galaxies of similar brightness. The scene remains peaceful now, yet the fingerprints of this slow feedback are written into the temperature and distribution of the group gas. From this extended, invisible cushion, the narrative can move back toward the starlight, focusing on how the luminous envelope and the central core of NGC 1600 reveal the reach of the black hole's gravity more directly. Moving inward through NGC 1600, the glow of the galaxy brightens smoothly at first, then begins to change character in a subtle, important way. In the luminous envelope, the fall-off of light with radius still follows the familiar patterns used to describe many massive ellipticals. Astronomers often fit this region with simple mathematical curves, and NGC 1600 largely behaves as expected there. The stars in these layers trace a gently steepening gradient with each step toward the center, bringing a noticeable increase in surface brightness. This behavior reflects how the stellar mass concentrates toward the middle, building a deepening gravitational well. For a long stretch, nothing seems unusual. The galaxy could almost be a standard example from a catalogue. As the view moves closer to the core, however, the trend shifts. Instead of continuing to brighten in the same way, the central profile begins to flatten. The light rises more slowly than the outer curve predicts, as though the inner galaxy resists becoming as dense as expected. A simple inward extrapolation of the luminous envelope would produce a sharp peak at the center. Instead, NGC 1600 presents a broad, shallow plateau. This quiet mismatch between prediction and observation carries deep meaning. It says that stars are missing from the innermost region compared with a galaxy that grew without special central disturbances. The area where the profile flattens is referred to as a depleted core. In NGC 1600, this core spans a surprisingly large physical scale, large enough that its size alone suggests a massive sculpting influence. The stars that now orbit within this region follow paths shaped not only by the overall mass of the galaxy, but also by the powerful pull of the central black hole. Even in sections where the black hole does not yet fully dominate the gravity, its presence has left a clear imprint. The missing stars and the softened rise in brightness both point to a past process that swept stellar orbits away from the center. A helpful way to think of this is to imagine starting with a galaxy whose inner light climbs steadily toward a sharp point. If nothing unusual happened, the final structure would preserve that steep rise. In NGC 1600 and similar systems, something has intervened. The inner stars have been stirred and scattered so that many no longer reside in the very center. Instead, they have been moved to wider orbits, thickening the envelope while thinning the heart. The result is a central region that looks gently carved, not violently torn, but clearly altered. The broad core, therefore, becomes a quiet witness to the galaxy's merger history. When two massive galaxies merge, their central black holes sink toward the middle of the newly formed system. They form a binary, a pair of black holes orbiting their common center of mass. Stars that pass close to this pair can be flung out through gravitational slingshot interactions, gaining energy at the expense of the binary. Over time, many such encounters eject stars from the densest region. Each interaction chips away at the central density, gradually expanding the core. When the two black holes eventually coalesce, the merged black hole remains, but the excavated region does not refill. The timescales for new stars to drift back in are long, and few mechanisms are efficient enough to rebuild the peak. In NGC 1600, the size and depth of the depleted core suggest that more than one major merger may have taken place. Each event would bring another central black hole into the mix, forming new pairs and repeating the clearing process. Layer by layer, the central light would be reshaped, turning a narrow cusp into the broad depression now observed. The luminous envelope outside the core records the accumulated debris and redistributed stars from those episodes. The core itself records where stellar orbits were most strongly rearranged. This relationship between the outer envelope and the inner plateau is essential for understanding why the black hole in NGC 1600 is so massive. The missing starlight represents a kind of currency spent during the mergers and the inward journeys of black holes. The more stars have been pushed outward, the more energy has been transferred from inspiraling black hole pairs. That transfer implies that large masses have participated in the dance. It becomes natural, even if still remarkable, that the final central object is measured at around 17 billion solar masses. From the perspective of the whole galaxy, the depleted core is not an absence but a signature. It shows that the innermost region is governed by more than just the smooth pull of the stellar body. It is the domain where the influence of the black hole becomes comparable to, and eventually exceeds that of the surrounding stars. This is the sphere where the black hole's gravity begins to shape not only orbits, but also the overall appearance of the light profile. The difference between the expected steep rise and the observed flat plateau can be mapped into an estimate of the total stellar mass that has been displaced. That mass in turn connects to the amount of work done by the black hole binary or binaries. In this way, the shape of the light becomes a gentle indirect measurement of the black hole's long-term activity. For a mental image, the luminous envelope and the core can be pictured as a hillside leading down to a broad, shallow basin, rather than to a sharp, narrow pit. The hillside represents the outer galaxy steadily brightening toward the center. The basin represents the core wide and relatively flat, with the depth set by how many stars have been moved outward. At the very center of that basin lies the black hole, invisible in the light but unavoidable in its gravitational influence. From here, the story naturally turns closer to that hidden presence. The next step follows how the motions of stars within and round the core reveal the sphere of influence of the black hole and allow its immense mass to be weighed, even though the object itself never appears directly. The depleted core of NGC 1600 is more than a gentle flattening in a graph. It is a hollowed-out region where the story of the galaxy's past becomes very clear. In this central zone, the actual starlight falls far below what a smooth inward extension of the outer profile would predict. The difference between expectation and reality can be translated into an estimate of how many stars once orbited closer in. That missing population is not destroyed. Those stars have been scattered outward, some lifted into the halo, some pushed onto wider elongated paths that keep them away from the deepest part of the potential well. In effect, the core of NGC 1600 is a cavity carved not by explosions, but by patient gravitational encounters. The key actors in those encounters are central black holes that arrive during major mergers. When two massive galaxies collide, each one brings its own black hole into the newly formed system. As the merger remnant relaxes, the two black holes sink toward the middle through interactions with surrounding stars. They eventually form a binary circling around a shared center in a tight dance. Every time a star passes close to this pair, gravitational slingshot effects can hurl it outward at higher speed. The binary loses some of its orbital energy and sinks deeper into the core while the star is promoted to a larger orbit. Over many such encounters, countless stars are treated this way. The process gradually empties the very central region, leaving behind a broad, low-density core. The size and depth of that core depend on how many mergers have occurred and how massive the black holes involved have been. In NGC 1600, both measurements point toward an unusually intense history of central scouring. The visible deficit of starlight implies that a huge mass in stars has been displaced from the middle. At the same time, dynamical modelling shows that the present black hole weighs in at around 17 billion solar masses. Together, these clues suggest that the core has been reshaped by more than one generation of binary black holes. Each time a new massive black hole fell in, and paired with the existing one, another round of stellar ejections would have followed, carving the core a little deeper and a little wider. Some stars that interacted with these binaries likely remain bound to the galaxy, now drifting through the outer envelope on long, slow paths. Others may have been given enough energy to escape entirely, becoming intergalactic wanderers in the wider group environment. Either way, their absence from the central light profile is recorded in the shape of the core. The galaxy today shows only the quiet aftermath of this activity. There is no sign of ongoing tearing or visible chaos in the starlight. Orbits have settled into a new balance, and the core has reached a stable form that changes only slowly with time. For a long interval now, the central black hole appears to have grown mainly by swallowing gas, rather than by swallowing other black holes. The earlier phase of frequent major mergers has faded into the background of cosmic history. What remains is a fossilized imprint of that era, preserved in the hollowed-out structure of the inner galaxy. This kind of core is not unique to NGC 1600, but here it is exceptionally prominent. Its large physical size means that the influence of the black hole extends over a region that would swallow the entire inner part of many smaller galaxies. The fact that the core is so wide and so flat, yet the outer galaxy still looks fairly ordinary, makes NGC 1600 especially informative. It shows that an ultramassive black hole can form in a host that otherwise resembles a standard elliptical in a modest group, The core becomes a gentle but strong reminder that the most important events in a galaxy's life may leave their clearest marks in the places where light is missing rather than where it is brightest. In the inner few thousand light years, every star that remains now orbits under conditions shaped by this history. The pattern of velocities, the directions of motion, and the degree of random stirring all carry the signature of past black hole pairs. These kinematic fingerprints allow astronomers to work backward, reconstructing how strong the central gravity must be to hold such a system together. The next step in the story focuses on those motions in more detail. By reading the speeds and directions of stars across the core and its edge, it becomes possible to define the true sphere of influence of the black hole and to weigh this unseen object with surprising precision. In that quiet, settled picture, the galaxy becomes a natural laboratory for gravity on extreme scales, yet nothing in the scene is rushed or violent now. From this hollowed heart, attention can drift outward again to the surrounding stars where measured motions patiently reveal the hidden mass that shapes their paths. The hollowed core of NGC 1600 invites a closer look at how its central mass is actually measured. Stars within and around this region move under the combined pull of the galaxy's body and the central black hole, and their motions quietly encode information about the gravity they feel. In this view, the stars become test particles drifting along orbits, whose shapes and speeds contain clues about the hidden mass that guides them. Astronomers cannot follow individual stars in detail at this distance, but they can measure how groups of stars move along the line of sight and across the face of the galaxy. With large telescopes and sensitive instruments, spectra are taken at many positions around the center. Each spectrum carries a blurred imprint of the velocities of countless stars. Where stars move quickly toward or away from the observer, absorption lines broaden and shift slightly. Where motions are slower or more ordered, the lines appear narrower. By mapping these subtle changes across the core and into the surrounding envelope, a field of stellar speeds and dispersions emerges. This map is not a picture of individual orbits, but it is a detailed portrait of how strongly the central region holds its stars. To turn this portrait into a measurement of black hole mass dynamic models are built. In these models, the luminous matter of the galaxy is described by the observed light profile, converted into a mass distribution with a chosen mass-to-light ratio. Around and within this stellar body, a dark matter halo adds an additional, more extended component. At the very center, a trial black hole mass is placed. Given these ingredients, many possible stellar orbits are calculated. Each orbit corresponds to a different path that a star could take in the combined gravitational field. Some orbits are nearly circular, others elongated, others tilted or box-shaped. That family of orbits can be mixed in different proportions to reproduce the observed light. The key task is to find a mixture that not only matches the brightness at every point, but also reproduces the measured velocity field. If the trial black hole mass is too small, stars near the center move more slowly than observed. The model underestimates the velocity dispersion in the innermost regions, because there is not enough central gravity to whip stars into faster motion. If the trial mass is too large, the opposite happens. Stars in the model move too quickly, and the predicted line broadening near the center exceeds what the spectra show. By adjusting the black hole mass and the orbital mixture together, a best-fitting model emerges. In NGC 1600, this careful procedure points consistently to a central mass of about 17 billion suns. The result holds even when different reasonable assumptions about the dark matter halo or the stellar mass-to-light ratio are explored. Many variations in the outer ingredients still converge on the same enormous central mass. This stability is possible because the radius where the black hole's gravity dominates is large compared with the scale that can be resolved by instruments. Sphere of influence is the term used for that radius. It marks the region where the black hole's gravitational pull outweighs the combined pull of the surrounding stars. In NGC 1600, the size of this sphere is comparable to the size of the depleted core. That overlap reinforces the picture built from the light profile. Where the starlight thins out, the black hole's gravity takes over. The stars that remain within this zone move in a potential shaped overwhelmingly by the central mass. Their high dispersions and particular patterns of motion cannot be explained without invoking a huge compact object. In this way, the stellar kinematics and the core structure support each other. One shows where stars are missing. The other shows how strongly the remaining stars are bound. Together they reveal the mass of an invisible giant without ever seeing it directly. For a gentle mental image, the central region can be imagined as a busy yet orderly sky of stars, each following a path curved by an unseen weight at the centre. Nothing dramatic happens on human timescales. Orbits complete in many millions of years, and the overall pattern remains steady. The sense of extreme gravity arises not from sudden events, but from the speed and tightness of these motions compared with the broader, slower orbits farther out. Each improvement in instruments sharpens this picture a little more, yet the basic conclusion remains the same. An immense compact mass must sit at the centre. The core of NGC 1600 therefore serves as a steady milestone in the study of black hole demographics, anchoring theories about how such giants assemble over cosmic time. The idea of a sphere of influence turns the abstract mass of the black hole into a concrete scale inside NGC 1600. Sphere of influence here means the region where the gravity of the black hole outweighs the collective pull of the surrounding stars. Within this zone, orbits feel the central mass most strongly. Outside it, the gravity of the stellar body and dark matter dominates. In NGC 1600, this radius is strikingly large, stretching over a region that encloses a vast number of stars and overlaps closely with the depleted core. That overlap is not an accident. It shows that the same gravity that governs the inner motions has also helped shape the distribution of starlight. At distances beyond this sphere, stars move mostly in response to the smoothed mass of the galaxy and the halo. Their paths resemble those in other massive ellipticals, with speeds set by the total enclosed mass on large scales. As orbits shrink inward and cross the boundary of the sphere of influence, the character of the motion shifts. The deep central potential begins to curve trajectories more sharply. Velocity dispersions rise and the mix of allowable paths changes. Stars on nearly circular orbits become less common. More follow elongated tracks that swing them past the centre and back out again. Many of the stars that once orbited completely within this sphere have already been removed by the processes that carve the core. Those stars were the ones most likely to interact with black hole pairs in earlier epochs. They supplied the encounters that allowed the binaries to lose energy and merge. Their absence leaves behind a region where the remaining orbits weave around a dominant mass that they rarely approach too closely. Today, the stars that still live inside this sphere move in a quiet, ordered disorder. They respond to the central mass like small leaves drifting in a deep, smooth whirlpool. Their motions are fast compared with those farther out, yet the overall pattern is steady. The balance between random directions and subtle preferred planes reflects the long history of mergers and relaxations that built the system. Each star now traces a path that is the outcome of countless past interactions. In this inner domain, the gravitational potential can be thought of as composed of three parts. There is the contribution from the stars themselves, the contribution from the dark matter halo, and the sharp concentrated contribution from the black hole. Near the centre, the last term dominates. If the black hole were somehow removed, the motions would change drastically. Speeds would fall and the structure of the core would no longer be stable. The fact that the observed velocities remain high all the way in confirms that a compact mass is present, and that its influence reaches out to meet the edges of the depleted region. The alignment between the size of the sphere of influence and the size of the core offers a gentle reinforcing picture. It suggests that the region within which the black hole controls stellar motions is also the region from which the largest number of stars have been ejected or relocated. The core is not simply a faint patch carved at random. It is the visible footprint of the zone where the black hole's gravity has been most effective over time. Beyond this scale, the ability of central binaries to throw stars outward weakens, and the galaxy resumes a more conventional structure. For a simple image, one can imagine a glowing lake of stars with a broad, shallow depression at its center. The depression marks the depleted core. Beneath that depression, hidden from direct view, lies the concentrated mass of the black hole. The sphere of influence is the volume within the lake where currents and flows are shaped mainly by this hidden mass. Outside it, the waters are stirred by the wider shape of the lake and the basin that holds it. Inside, every movement feels the steepening pull of the central depth. In physical units, the radius of influence in a galaxy like NGC 1600 can reach thousands of light-years, a scale large enough to encompass entire smaller galaxies. That size emphasizes just how massive the central object must be. Only a black hole with billions of solar masses can hold sway over such a volume. This scale also means that the region where relativistic effects begin to appear in the strict sense lies much deeper in. The event horizon itself is tiny compared with the size of the core and the sphere of influence. There is a great deal of space between the radius where the black hole dominates stellar motions and the radius where light can no longer escape. In that broad intermediate zone, gravity is strong but still gentle enough that stars and gas can follow long-lived orbits. Tidal forces there are powerful but not instantly destructive for objects at typical densities. This separation of scales brings a quiet reassurance. The galaxy can host an extraordinarily massive black hole without becoming a place of constant extreme events. Most of the time, stars glide around peacefully even while moving under a gravity that owes much to a compact central source. In NGC 1600, the sphere of influence therefore acts as both a dynamic and a structural boundary. It marks where the black hole's presence shifts from background contributor to primary shaper. It also marks where the visible imprint of past binary interactions is strongest. From this boundary inward, the story gradually transitions from classical orbital dynamics toward a regime where space-time curvature grows more pronounced and where even light begins to follow more twisted paths. The journey will not cross the horizon, but it will move closer to the region where orbits approach their innermost stable form and where the concept of a simple flat stage for motion starts to break down. Seen in visible light today, the center of NGC 1600 looks calm with no obvious sign of a blazing engine. The galaxy's core glows steadily, but it does not dazzle with the fierce brilliance of a quasar. In radio and X-ray views, the story is similar. The emission from the nucleus is present but modest, hinting at a black hole that feeds slowly, if at all, on the surrounding material. Yet the mass inferred for that black hole tells a different, deeper story. A central object weighing billions of suns cannot have reached its current size by quiet nibbling alone. At some earlier time, it must have grown much more rapidly, drawing in gas at a high rate and releasing large amounts of energy. That more active era would have turned the nucleus into a luminous beacon, even if only for a limited span of cosmic history. The present quiet state therefore carries a memory of past storms like a calm sea that still holds the deep shape carved by old currents. During such an active phase, gas spiraling toward the black hole would have formed an accretion disk, a flattened rotating structure heated by friction and compression. Accretion disk here simply means the bright hot region where inflowing material orbits before crossing the final gravitational thresholds. In that stage, radiation from the inner disk could have outshone all the stars in the host galaxy, especially at shorter wavelengths. Outflows driven by this radiation and by magnetic processes near the event horizon would have pushed back against the surrounding medium. Jets may have pierced the group's hot gas-inflating cavities and stirring turbulence on scales much larger than the galaxy itself. These processes are now stopped or greatly reduced, but their long-term effects linger in the temperature and structure of the group atmosphere. Over time, the intense outpouring of energy during active phases can heat gas that might otherwise cool and fall inward. In NGC 1600, the extended halo of hot group gas and the low rate of current star formation both point toward such a history. The central galaxy contains mostly old stars and little cold gas. That combination suggests that earlier episodes of black hole growth helped to shut down the supply of fresh fuel for starbirth. The energy released in those phases did not strip the galaxy bare. Instead, it appears to have raised the temperature of the surrounding medium just enough to slow the inward drift of new material. The result is a long-lived, gently balanced state. The galaxy remains massive and red, and the black hole remains enormous, but neither now burns with the intensity of its youth. For a quiet mental picture, the inner region of NGC 1600 can be imagined as a hearth, where the main fire has long since died down. The coals are still warm, emitting a faint glow, but the furious blaze that once reshaped the room is gone. The wall ceiling and air remember that earlier heat in their settled temperatures and in the patterns of smoke that once curled upward. In the galaxy, the equivalent memory resides in the lack of young stars, the shape of the hot gas, and the depleted core that carries the marks of earlier black hole pairings. Even now, the central engine may flicker at a low level. Small amounts of gas could continue to drift inward, perhaps from slow stellar mass loss in the core or from minor interactions with satellites. When such material reaches the inner regions, it can light up the nucleus, briefly producing a faint active galactic nucleus rather than a quasar. Short episodes of increased activity may come and go over millions of years, never approaching the pass peak but still contributing a little to the long-term energy balance. These gentle flares fit into the broader pattern of feedback between the black hole and its environment. Each time the nucleus brightens, it sends energy outward into the surrounding gas. The gas warms and resists further inflow, and the supply of fuel to the black hole diminishes again. In this way, the system regulates itself without needing constant extremes. The huge mass of the black hole ensures that even modest accretion can produce significant energy, so the feedback loop can operate efficiently at low levels. From a broader perspective, NGC 1600 illustrates how a galaxy can pass through a luminous quasar phase and then settle into a long, quiescent stage, while still carrying the imprint of that earlier growth. The ultramassive black hole no longer announces itself through blinding radiation, but through the motions of stars, the shape of the core, and the properties of the gas. The present calm does not contradict the past intensity. Instead, it completes the picture of a life cycle in which brief active periods are followed by extended, gentle aftermaths. In the context of the larger universe, this system hints that many other apparently ordinary groups may hide similar giants' relics of bright phases that ended long ago. Their signatures may be subtle, visible only in carefully measured kinematics and faint X-ray halos. In that sense, NGC 1600 is both special and representative. It stands out because its black hole mass is unusually well measured and extremely large. At the same time, it may be a member of a broader, mostly unseen population of quiet giants. From this idea of a quasar memory in a peaceful galaxy, the path narrows further toward the region where gravity becomes strongest. The narrative now turns to the inner domain of orbits near their innermost stable forms, where space-time curvature begins to shape not just speeds, but the very geometry through which light and matter travel. The idea of feedback links the quiet center of NGC 1600 to the wider group in a single long conversation between gravity and energy. Feedback here simply means the way energy released near the black hole changes the behavior of gas on much larger scales. Over cosmic time, this exchange has shaped not only the fate of the central galaxy, but also the thermal state of the entire halo. The hot gas that fills the group carries the imprint of that history in its temperature, density, and gentle motions. Without any feedback, the gas would cool steadily, radiating away energy as X-rays and drifting inward under gravity. As it cooled, it would condense into denser clouds, eventually forming new stars in the central galaxy and delivering a fresh, steady supply of fuel to the black hole. The system would brighten in bursts of star formation and nuclear activity. Instead, observations suggest a slower, more regulated pattern. The gas remains hot over large volumes, and the rate of new star formation in NGC 1600 is low. This indicates that at key times in the past, energy from the growing black hole has reheated or stirred the gas, preventing it from collapsing too quickly. During active phases, jets and outflows from the region near the event horizon can plow into the surrounding medium. They inflate bubbles where the gas is thinner and warmer, and they drive weak shocks that travel outward. Over millions of years, these effects lift and mix the intragroup gas. The detailed shapes of these structures are subtle at the distance of NGC 1600, but the overall pattern is familiar from similar systems. Where bubbles rise cooler, gas may be dragged outward, spreading fresh material through the halo. Where shocks pass, they deposit small amounts of heat. None of these events are explosive on the scale of the group. They are more like gentle repeated pushes that keep the gas from settling into a simple, steady inflow. In quieter intervals, when the nucleus dims, the heated gas can begin to cool again. It radiates away the energy gained from past outflows, slowly drifting back toward lower temperatures. As it does so, some of it may start to move inward once more. If enough gas reaches the central region, the black hole brightens again, producing another round of feedback. The result is a cycle that oscillates between mild inflow and mild heating rather than a one-way collapse. For a listener picturing this process, the group atmosphere can be imagined as a deep, warm pool in a wide valley. Gravity tries to let the water settle and run toward the center. At intervals, gentle stirrings from below send waves and ripples through the pool, keeping it from becoming completely still. The surface remains mostly calm, yet the mixing prevents the water from forming narrow, fast streams. In NGC 1600, the deep concentration of dark matter in the halo helps the feedback loop operate over long time scales. The strong gravity holds the hot gas in place even when it is stirred, preventing large amounts from escaping into intergalactic space. This means that energy injected by the black hole remains trapped within the group environment, where it can be reused again and again to resist cooling. The system becomes a nearly closed reservoir of gas and heat, gently tuned by the central engine. The evolutionary consequences of this balance are far-reaching. Because the gas does not collapse rapidly, the group does not build many new bright spiral galaxies. Instead, existing galaxies age and fade, their stars growing older, while only small pockets of residual star formation continue. NGC 1600, sitting at the center, grows mainly through mergers and slow accretion, rather than through repeated bursts of in situ star birth. The black hole grows mostly during earlier phases when more gas was available, and the feedback cycle may have been more intense. In the long quiet that follows, the giant black hole continues to shape the group, mainly through its past actions now frozen into the structure of the halo. This combination of deep halo hot gas and a dominant central galaxy gives the group a fossil-like character. It appears as a mature system, where the most dramatic changes have already happened. The bright central elliptical carries the memory of many merged companions. The hot atmosphere remembers earlier heating. The outer satellites trace the few remaining pieces that have not yet been fully absorbed. The group seems to have run much of its course, yet it still evolves slowly as time passes. Gradual infall of small galaxies continues, and the gas reservoir slowly thins as it radiates energy away. Far into the future, NGC 1600 may become even more dominant as more companions merge into it. The black hole may gain a little more mass from occasional gas inflows and minor black hole mergers. However, the broad outlines are already set. The galaxy will likely remain a massive red elliptical in a sparse group, with a very large central black hole and a quiet halo of hot gas. On human and even civilizational timescales, nothing about this grand balance will change in a way that affects distant observers. For those watching from afar, the system stays serene, a steady glow, with only slow, almost imperceptible shifts in brightness and structure. The feedback that once roared now persists only as a faint murmur in the gas and as a pattern in the group's layout. From this perspective, the role of the black hole broadens beyond the immediate core. It becomes an architect of the group's long-term character, deciding how quickly gas cools, how often new stars appear, and how long the galaxies remain quiescent. In NGC 1600, that architect has favoured a path of early strong growth, followed by a very long period of rest. From this wide thermal view of the system, the focus can now return inward again toward the region, just outside the event horizon, where space-time curvature shapes not only the paths of stars and gas, but also the routes taken by light itself on its way out to the wider universe. Closer to the centre of NGC 1600, distances that look tiny on the sky still cover immense regions of space. A shift of a single arc second corresponds to thousands of light years at the galaxy's distance, yet the narrative now steps down to scales far smaller than that. Within the depleted core and inside the sphere of influence, orbits begin to respond almost entirely to the central black hole. Stars, gas clouds, and any drifting dust follow paths that curve through a gravitational field far steeper than the one felt in the outer halo. The sense of depth increases the nearer the view moves toward the heart, like walking down a long, gentle slope that gradually becomes a smooth basin. In this inner domain, classical gravity and the curvature of space-time blend into one description. Space-time curvature simply means that the presence of mass changes the straightest possible paths that objects and light can follow. Near a black hole as massive as the one in NGC 1600, those paths bend noticeably over quite large distances. Orbits that might have been wide ellipses in a weaker field become tighter, slowly rotating loops here. The closer an orbit lies to the centre, the more strongly it feels these effects. For matter that reaches the region where an accretion disk would form the structure of space-time itself, dictates what kinds of circular paths remain stable. There exists a special radius called the innermost stable circular orbit. Inside this innermost stable circular orbit, or ISCO, circular paths are no longer safe. Material that drifts inward past this boundary cannot maintain a steady ring. It must either plunge inward or move in rapidly changing tracks. Outside the ISCO, orbits can still be relatively calm even in the presence of strong gravity. The exact location of this boundary depends on the spin of the black hole. If the black hole rotates the space around, it can be gently drawn into motion, a phenomenon known as frame dragging. Orbits that move in the same direction as the spin can exist a little closer in than those that move against it. For the present purpose, exact numbers are less important than the picture. There is a narrow zone where stable motion ends and inward plunge begins set by the mass and spin of the central object. Slightly farther out lies another important shell known as the photon sphere. Photon sphere means the thin region where light itself can orbit the black hole on circular paths. Any small disturbance sends photons either outward to infinity or inward toward the horizon. Even so, the existence of such orbits adds a delicate ring to the structure of spacetime around the black hole. In NGC 1600, the illumination is faint today, but the geometry still exists waiting quietly in the dark. Between the photon sphere and the ISCO orbits for matter are still possible, but increasingly constrained. Gas clouds or clumps that wander into this regime would feel strong tidal forces and rapid precession, yet they would not be torn apart instantly unless they venture much closer still. Tidal forces here simply describe how gravity pulls more strongly on one side of an object than the other. For dense stars, those forces at these radii remain tolerable. They can complete many orbits without disruption. Time also behaves differently in this deep region. Gravitational time dilation means that clocks closer to the black hole tick more slowly compared with clocks far away. Signals climbing out of the potential well lose energy and appear redder, a process called gravitational redshift. These changes are gentle for light leaving the outer parts of the core, but grow more pronounced near the boundary of stable orbits. A pulse emitted near the ISCO would arrive at great distance stretched and softened, carrying a quiet record of the depth from which it came. For a calm image, the innermost region around the black hole in NGC 1600 can be pictured as a nested set of invisible shells. The outer shells mark the sphere of influence and the edge of the depleted core. Closer in lie shells where orbits precess rapidly, where circular paths cease to be stable, and where light itself can slide briefly around the center before escaping. At the very center sits the event horizon, the notional surface beyond which escape is impossible. Event horizon here simply names the boundary of no return, not a solid wall. Nothing in this arrangement suggests sudden violence at the boundary itself. Space-time and matter simply follow the rules of general relativity, more strictly as the center is approached. In NGC 1600, this entire structure exists in relative quiet. The lack of a bright accretion disk means that most of these shells are dark. Their presence is known not from their glow, but from the way they would shape any passing light and any infalling matter. The description therefore lingers just outside the final boundary in the region where orbits nearly fail, and where light still carries news back to the wider universe before fading into space. From the outskirts of the group to the silent boundary of the event horizon, the structure of NGC 1600 now stands as a single-layered whole. A sparse collection of galaxies drifts within a deep dark matter halo, wrapped in a pool of hot gas that glows softly in X-rays. Within that halo, the outer stellar envelope of NGC 1600 stretches far beyond its bright core filled with ancient stars that remember many earlier mergers. Faint shells and streams trace the last steps of swallowed companions, while the diffuse halo records those that vanished much earlier, their identities dissolved into the common light. Moving inward, the galaxy settles into the familiar form of a massive elliptical smooth brightness, gradients, old stellar populations, slow rotation, and strong velocity dispersion. In that region, NGC 1600 behaves much like a textbook example, fitting the patterns that tie stellar mass light profile and internal motions together. Only deeper inside does the galaxy begin to reveal how far it truly departs from those calibrating cases. The broad, depleted core marks the first clear sign that something unusual has happened. Instead of climbing toward a sharp central peak, the brightness levels off into a wide plateau. The missing light there stands for stars that were once more tightly bound, then gradually lifted outward by the repeated passage of black hole binaries. Each major merger brought a new central object into the core, and each pairing flung stars away through gravitational encounters. Those encounters hollowed the heart of the galaxy, while at the same time building the mass of the central black hole to extraordinary levels. Stellar kinematics weave the same story in motion. High dispersions near the center and characteristic patterns in velocity maps demand a very deep central potential well. Dynamic models that combine the light distribution with many possible orbital families converge on a black hole mass of roughly 17 billion suns. The radius where that mass dominates stellar motions coincides closely with the size of the depleted core, tying together structure and dynamics. Within that sphere of influence, stars follow tightly curved paths in a gravitational field that is no longer gentle, yet still smooth and predictable. Beyond the galaxy, the wider group bears the long-term imprint of the same central engine. Hot gas remains suspended in the halo, neither collapsing rapidly nor flowing away into space. Earlier bursts of nuclear activity heated and stirred this gas, slowing its cooling and regulating the supply of fresh fuel. The result is a mature, quiet group where new star formation proceeds only at a low level, and where the central galaxy remains red and old. Feedback between the black hole and the gas has guided the system toward this balanced state, with early intense growth followed by a long, gentle afterglow. On the smallest scales, the geometry of space-time around the black hole introduces additional layers that cannot be seen directly but can be clearly described. Within the inner region, stable circular orbits give way to paths that precess and wobble, then finally to the innermost stable circular orbit, where matter can still circle briefly before beginning an inward plunge. Deeper in lies the thin photon sphere where light itself can loop around the black hole on fragile orbits, sensitive to the faintest disturbance. At the very center sits the event horizon, a smooth, invisible boundary past which paths no longer lead back to space. This final surface does not announce itself with a shock or a wall. It simply marks the place where the shape of space-time curves so fully inward that escape is no longer possible. For NGC 1600, this horizon remains far beyond direct observational reach. Its existence is inferred from the mass from the motions of stars and from the success of general relativity in describing similar systems. The narrative therefore stops comfortably outside it at the edge of the description-forbidden core where observations still speak clearly and theory remains firmly anchored to measurable quantities. From that vantage, the entire system can be viewed at once. A concentrated dark halo gathers galaxies and gas. A massive elliptical sits at the center, its outer envelope smooth, its inner core gently carved. An ultramassive black hole resides within that core shaping orbits and light profiles over thousands of light years. The hot atmosphere records the energy released during past active phases, and the quiet present shows how those phases have long since softened into calm. Nothing about this arrangement demands alarm. The galaxy and its black hole have already completed the most dramatic parts of their shared story. What remains is a stable configuration that will change only slowly on timescales far longer than any human span. NGC 1600 becomes a calm example of how gravity, gas and time work together to build a system where a 17 billion solar mass black hole can rest at the heart of a seemingly modest group. The observational journey ends at the point where instruments can still trace starlight and gas, and where the mathematics of curved space-time can still be tied back to data. Beyond that lies a region left deliberately unpictured, allowed to remain a quiet interior that does not need to be crossed. From the outskirts of the group to this gentle boundary at the core, the path has closed into a loop, returning to the simple idea that a calm, ordinary-looking galaxy can harbour a hidden giant, and that this giant can shape its surroundings without breaking the deep, steady quiet of the night sky. The journey through NGC 1600 settles now into a gentle stillness, as if the galaxy and its group were exhaling after a very long breath. Far from Earth, the sparse collection of galaxies continues its slow dance inside the dark matter halo, wrapped in a faint warm fog of hot gas. NGC 1600 rests at the centre of this structure like a quiet lantern, its old stars glowing steadily, its outer shells and streams barely visible against the background. Deep inside, the broad depleted core holds its hollow form, and the ultramassive black hole rests within that space-shaping orbits and light without calling attention to itself. Nothing in this scene changes quickly. The hot gas cools in slow motion. The satellite galaxies trace wide loops that take hundreds of millions of years, and the stars in the core glide around the hidden center on orbits that will not complete in any human lifetime. The former storms of accretion and feedback that once brightened the nucleus now survive only as patterns in the gas and as the settled shape of the galaxy. What remains is a calm system where gravity, memory, and time share the work. From the edge of the group all the way down to the brink of the event horizon, every layer fits within this quiet picture. The dark halo, the glowing gas, the smooth envelope of stars, the carved-out core, and the invisible giant at the heart all hold together in a single stable arrangement. The night sky above Earth shows NGC 1600 as just one more distant glow among many, yet within that point of light lies this entire structure resting in deep equilibrium. As thought drifts back outward away from the group and its hidden gravity, the image of the galaxy can soften into a simple idea once more, a calm ellipse of light far away, carrying a story that has already unfolded and continuing its slow, steady existence in the quiet dark.